Okay, so welcome back. This is Chapter 2, Geography 101 at Cal State Northridge with me, Dr. Graves. This unit is about Earth-Sun relationships. We'll talk about the Sun for a while and then the Earth's relationship with it as it travels an orbit around the Sun. For this week, the things you ought to do is first read the chapter before you even really watch this video and take notes while you're reading because it helps you remember. Take this quiz after you have read the chapter to test your ability to remember what you have read. You can take it a couple of times, so make sure you get a good score. And then after you've done that, watch these lectures. And while you're watching these lectures, take notes for the online exam that you will have later. Also note that there are some resources, there are some videos that you can watch to supplement what you've read and what you're hearing and watching right now. But also take some time very soon to prepare for the very first map quiz, which is a map quiz over California's physical features. There's a list of places to know. Take the quiz, the practice quiz, and then you'll notice that at a date very soon, there's the actual map quiz. All of this information and the dates and the due dates are available on Moodle either in the upcoming events block or in the calendar block. And remember, you can download. So let's turn our attention to Earth-Sun relations. Now here are the PowerPoints, and they're available online as well through Moodle. So if you want your own to print out and to annotate on your own, then you are more than welcome to do that. So these are the learning objectives, the things you're supposed to know for this semester. And I'll let you look at these quickly on your own, but I do want to suggest to you that the first group of these really are necessary for you to understand the ones down here: solar altitude, declination, day length, and really this is our point. Why are there seasons on Earth? So let's back up way out and take a look at a view of the Milky Way, which is our galaxy that we live in. You can see it at night, perhaps not so well here in Los Angeles where there's a lot of light pollution, but if you go out to the desert or some place where there aren't very many street lights, then you can see the Milky Way as a massive cloud of tiny points of light across the sky. We are one of those points of light, or rather our sun is one of the points of light. It's an ordinary galaxy. It's an ordinary star, our sun, and we are certainly an ordinary planet. The distances in the known universe are mind-boggling. They're staggering, and they're so great that we can't use things like miles or kilometers very well to describe the distances because the numbers would just be too absurdly large. So we use something called a light year, which is the distance that light travels, say a particle of light or a train traveling at the speed of light would travel in a single year. 300,000 kilometers per second. The train would go 9.5 trillion kilometers at the speed of light if it was going for 1 year. So it is a unit of distance, like a mile or a kilometer, but it is used for these massive distances. So here's us, this tiny little spot in our solar system, and here's our solar system in just the Milky Way. It's 100,000 light years across. And you see, if you were to multiply 100,000 by 9.5 trillion kilometer, so you would have a number that was absurdly large and hard to express. I've seen this here. Here we are somewhere in just the Milky Way, and there are millions of galaxies similar to the Milky Way, some very much larger in the known universe. Zooming in a bit, the Earth goes around the sun in an elliptical fashion. That means that it's sort of an oval rather than a perfect circle. It's not too far off a perfect circle, and we stay on a plane called the plane of the ecliptic. All of the other planets are also on this plane, and so it's like we are a speck of dust on a record or a CD that is spinning around. We're about 150 million kilometers from the sun, and it takes the sun's light about 8 minutes to get to us. Now, sometimes, and I'm going to exaggerate this in the drawing up here, the Earth is here, and when we are closest, or I should say this is the sun, so that's the sun, and the Earth is going around this plane of the ecliptic. We are at perihelion in January, and we are at aphelion in July. So we're further away in July as we go around the Earth. Now there are some videos online, and I've posted them in YouTube that you can watch on this that do a much better job of explaining it, but it seemed absurd to put a video inside a video, so I'll let you do that. The next bit is energy that comes from the sun. And the sun is this huge mass of helium that is being turned into hydrogen, causing enormous nuclear explosions and energy going off all of the time. And that energy comes to us as light and heat from the sun. Here's a picture of the sun, the Earth, and just how large it is compared to a solar eruption, some of which show up as these sunspots. And part of the reason we want to know about the sunspots and these solar storms is that they have an effect on us. The sun produces something called a solar wind. These are particles that are ejected from the sun and go outward across the solar system. It takes about 3 days for these particles to get to us, and when they do hit the Earth's outer atmosphere, something called the magnetosphere, which is the magnetic force field that is around the Earth, deflects that solar wind at the poles, and only a small portion of it actually enters the atmosphere. When it does, it produces auroras, which you've heard of, perhaps the northern lights, or in this case the southern lights. Here's Antarctica in the middle, and this are these charged particles hitting the Earth's atmosphere and interacting with the Earth's magnetic field. From the ground, this is what it might look like. This is the aurora borealis, or the northern lights, somewhere over Canada. Occasionally you can see it in the lower 48 states. I've witnessed it several times on really cold days in over Lake Erie or up in northern Michigan. It scared the crap out of me, to tell you the truth, the first time I saw it, because I didn't know what was going on. All of this nuclear energy that's being produced inside the sun is radiated outward from the sun across a spectrum of energy. It comes to the Earth, takes about 8 minutes to get here, and it comes in different wavelengths. Short wavelength, which is a great deal of what comes to us, is emitted by the sun because it is very hot. This shortwave radiation comes with high temperature. The sun is hot. The Earth emits mostly long-wave radiation because the Earth is not a particularly warm body in space. It's important that you understand that there is energy coming in from the sun, hitting the Earth. A great deal of it is filtered out by the Earth's atmosphere. There is some that does get to us in the visible light range, and then there it is turned into what we know as heat, or what we feel as heat, called long-wave radiation, and that escapes back. It is very important that the amount of energy that is coming into the Earth is equaled by the amount of energy that is going out. If one overwhelms the other, the Earth either heats up too much or would cool off too much for life to be sustained. This solar radiation that reaches the Earth's surface at any place is called insolation, and it's a portmanteau of three words: incoming, solar, radiation. And so when I use the term insolation, that's not insolation with a U, but with an O. And this is essentially the energy that is coming from the sun to us. It arrives at the top of the atmosphere 1,372 watts, like a light bulb, across a square meter of space. So that's a lot of energy, and if we could just convert that to electricity, we would have more than enough for everybody to do everything for all time. Now we get a lot of this energy from the sun, heats up the upper atmosphere, but we only get a tiny fraction of the sun's total energy output. Most of the, or a good chunk of this energy that does come to Earth is in the tropics, meaning in near the equator and the tropics of Cancer and Capricorn. The areas with near the equator receive more than 2.5 times the total energy that the North and the South Pole receive. And that's because the Earth is most, or the Earth receives the most direct sunlight between the Tropic of Cancer and the Tropic of Capricorn. So the more direct the sunlight, the more direct this energy, the more intense that it is. Up here at the North Pole, the sun's rays are most oblique, meaning that they hit at an angle which deflects the intensity. Think of it as being hit by a baseball. If you're to be hit directly, it would hurt a lot more than if you were to be hit as a glancing blow. The place where this energy is most directly landing on the Earth's surface is called the subsolar point. You have to have that vocabulary in your back pocket so that you can reference it later. Note that these graphics, that at the poles they receive essentially no, this is the North Pole, no energy from the sun during the long winter months, and a great deal during the summer months, but that is similar to what the equator is receiving pretty much year-round. Here's the South Pole getting virtually the opposite insolation as the North Pole. This is a measure of the average daily net radiation exposed or expressed on a map. Note that on average these areas over the ocean receive the most net radiation, meaning they're getting more than they're losing. These areas here are cold because they lose more radiation than that they get. The only curiosity here is really the Sahara Desert, and that it has an actual net radiation loss, which would make you think that it is cold there, but that is a measure of its albedo. You remember that from the last lecture. The albedo is the reflectivity of the hot sands of the Sahara, whereas the areas that have either lots of leaf matter, like the rainforest, or certainly the ocean, are absorbing more of that energy. Lots of albedo also in the polar caps, so reflecting a lot of that energy back out. And that ends this segment of this lecture.